potential depends on all the moduli. Is non-perturbative. So, the superpotential in general is quite complicated. It involves membrane instantons and strong gauge dynamics. But the leading contributions to these terms, in the case of strong gauge dynamics, are simple exponentials. And even though there could be all these other terms, every term is an exponential, and we, for the purposes of being able to calculate something, we simply assumed that the leading contribution were two non-perturbative terms. In fact, we can show that one non-perturbative term is enough, but the vacuum you get is beyond the supergravity approximation, so you can't trust it. And it turned out that having two or more, which is actually much more generic and more representative of these vacua, because we want to try and make as general a statement as we can about the physics of this particular corner of the landscape. So having more is more generic, and the superpotential for each such contribution looks like this, where these coefficients are actually constant, and in many cases you can calculate them. They receive contributions from threshold corrections to the gauge coupling, which has been calculated by Friedman and Witten. So they can vary in the landscape. But we took them to be, say, order 1, or the ratios of them to be, say, order 10. There are integers which tell you the homology class of the free cycle, which we took to be of order 1. And then there's the ranks of the gauge group, or more generally the dual Coxeter number of the gauge group, which are not so big. We just took them to be maximally order 10. This is the form of the Kähler potential we use. It's an n parameter family of Kähler potentials, where n is the number of moduli, and it's arbitrary at this point. This form of the Kähler potential is an assumption. In general, it could be a scale invariant function inside this log, but this is known to reproduce. This is known to be the Kähler potential for certain simple examples, and I think it's a reasonable assumption. But this is an assumption that can be questioned once we have more information. No, if you turn on fluxes, you get a large contribution to the superpotential. We wanted to avoid fluxes altogether. We want all the moduli dynamics to be generated non-perturbatively in order to generate a small scale. So we can compute this. We can write a formula for the potential, and it's very complicated. So the first thing we did was minimize this potential numerically. Well, there was some. We did have some at initial stage partially analytic results. Yeah. The other ones are axioms, so they're not moduli, they're compact. So any... Yes, but axioms are compact moduli, so any higher order correction will generate a minimum, because it's a function on a compact space. So the results of this numerical analysis showed that there are indeed metastable vacua with all the moduli fixed. But after some long staring at the formulas and so on, actually Constantine was able to find analytic formulas for the solutions. Now this is just writing this down just to give you an idea of what the moduli beds look like. An expansion in this log of the ratios of those numbers. So once you have that, you can go ahead and calculate things like gravitino mass, scalar masses, gaugino masses, etc. And this is the formula you get for the gravitino mass. I'm just writing it down just to prove to you that we actually did it. And so, if you take the choice, choose some reasonable values for these numbers, that gives the gravitino mass of about 2 TeV. The scalar masses